All right, it's time. Before we continue, I received some question from one of you guys talking about chaos system. So technically, this one is in 2.8. You can read about it, and it's not covered in the course content I received, so we chose not to go over it. So the first thing I can do is I put a link in the chat channel, so you can go ahead and look for yourself. It's basically a short video made by a really nice lady, and she explains what chaos system is and also how to quantify chaos system roughly. And if after that you have some interest or you feel like you want to hear more about chaos system, just send me an email and I will see if I can squeeze in another section talking about chaos system at the end of the semester. Okay, so for now, just watch the video and see if you want to know more. Okay, if a few people want to know more, of course we can go over it. Okay, now let's go back to what we have here on the linear systems. We talk about dy over dt equals a times y, where a is a matrix. So basically we have a linear system and everything here is just nothing but constant. And last time we talked about, for two-dimensional system, which means your a is 2 by 2, we do need to just find y1 and the y2, where y1, 0, and y2, 0, okay, are linearly independent. Okay, once you have that, what you can do is you can write down the general solution to be like y equals k1, y1, plus k2, y2, where k1, k2 can be any constant. So that's basically a way for us to find the general solution of linear systems. Any, any constant. Okay, we are very familiar with this. It's basically finding two linearly independent vectors, and then the general solution will be the all possible linear combinations of this. Okay. With that in mind, we solve the y prime prime equals negative y, which is a harmonic oscillator, non-damped, and we have y prime equals v, v prime equals negative y. We got a matrix. Then we say, well, to solve this one, we just need two linearly independent solutions, which we already know, sine and cosine. T. We basically just did it by guessing. Okay. Once we have this, then all possible solutions is nothing but k1 plus k2. Okay, so you may have some solution look like this, for example. But more or less, it will be some format with only a difference of constant. That's what the linear principle gives us. All right. Another example we can quickly show. A system look like this. Let's just do y. Example. Well, how to solve it? Again, we need two solutions, just the two linearly independent solution. Then the rest will be all possible linear combinations. So if you think about it, we can look at and determine this is partially decoupled. Okay. As long as it's partially decoupled, we can solve 2 first. That gives you y equals constant times e to the negative 4t. Plug this one back into 1. Times the 3. Now we see the advantage of decoupled system. Once you put the y in, now this one has only something to do with x. You can solve it whichever way you want. I would just say it's a linear. So we times the integrating factor, which is e to the negative 2t. Then we have e to the negative 2t times x prime equals this, which gave us x e to the negative 2t equals 3c e to the negative 6t negative 1/2 plus a d. X equals d e to the 2t. All right. Sounds good. Partially decoupled system. We can solve it by old knowledge. Of course. Now what we can do is put them together. Your final y equal. Your x is this. Your y is this. Okay. Which is by vector decomposition, and then you can see you can take out a constant, that is c. And what you have here is e to the negative 4t, e to the negative 4t. You can times the 2, so negative 1 and the 2. Moreover, you can change this to be k1, k2, because they're basically any constant. Okay, so you can see, okay, it's all the possible linear combination of 2 linearly independent solutions, this and that. Why? because when you plug in 0, y1, y2. When you plug in 0, when you plug in 0, are they linearly independent as a vector? Well, you know it's linearly independent. You can draw these two vectors. They're not on the same line. Therefore, this will be the general solution. Okay, so even if you solve everything and have a general solution look like this, but if you clean things up a little bit, you realize, oh, this is nothing but all possible linear combinations of two linearly independent solutions. Then the same principle works. Does everything make sense so far? This is clearly not the best way of solving it. We wish we could solve it on a matrix format, not just one by one, right? Later, we will show you how to actually solve it just at the vector level, so you don't have to go into it and solve one after another, and then clean things up. You can actually do it directly. Okay, so that's all the setup. Now we kind of know if we have a linear system, we're looking for, if you have a 3 equation, we're looking for 3 independent solutions, then all possible linear combination. If you have a 2-dimensional system, then 2. If you have a 5-dimensional system, then 5. As long as it's linear, this is going to work. The rest is try to go ahead and try to find how to do it. Okay. We have a whole chapter of how to do that. So the first thing we talk about is the straight line solution. Okay. To see that, let's take the example we just did. We have this y equal prime 2, 3, 0, negative 4y, which we just finished. All right. Now let's draw the phase portrait. Okay. This is the system. Okay, take a look at here, 2, 3, 0, negative 4, 4. We know how to do the phase portrait, so let's do it. Once we finish, the phase plane looks like this. It's kind of messy. Let's make it. Okay. What happened? Well, you do have the phase plane portrait. You can trace all the solutions. But do realize there are 2 lines, which I marked here, the green line and the orange line. These 2 lines are special. What's special about them? That means if you start, your initial value is on this green line, you stay on this green line. Okay? If your initial value is on the orange line, you stay on the orange line. If you are anywhere else, then you follow whatever the trace take you. But these 2 special lines is what we call a straight line solution. Make sense here? What we want to do in this section is, given a system, we want to know how to find these straight line solutions. Once we have that, later we will try to show all other solutions are nothing but a linear combination of these 2. So you have all the solutions. That's what we're trying to do. let's focus on the straight line first. Okay, so this is what we did with the face portrait. Ooh. We have all the solutions look like that. Okay, that's fine. But we do have two lines. One is here, one is like that. For these two lines, once you start from it, you stay on it. Okay. Now go back to what we just did. For the system, we solve the solution. Let's copy it. Y equals K1. That's the solution we got from last time, right? Now, do you see a point of writing these two in this way? Because these two factors are the same, we can actually take it out. Now, if you take K1 equal to 0, and you take K2 equal to 0, you do have two special solutions. The first one looks like this. I mean, it works for any K1, K2 you pick. Of course, you pick one of them to be 0. It's still a solution, right? And what's special about these two? Do you realize if you plug in different t, this one will change, but this stay the same? What is that? That is a constant times a vector. What is a constant times a vector? That will be the multiple of the vector. Make sense here? That means this one stays on a straight line because you're basically a vector times different constant. So no surprise, one of the line is 1, 0. In this direction of 1, 0, that's this line. And no surprise, the other line is going to be the line in the direction of this vector here, -1, 2. Because when you change your solution that's t, you basically change a constant times a vector. That's why it works. Make sense so far? It's easy once you have it. The problem, of course, is from the beginning, how do you know which vector? How do you know which vector will give you a solution like this? Okay, well, let's write down. This becomes interesting. Your solution can be anything. No problem. Okay, but the straight line solution will be special. It will look like this. Equals a constant times a vector. And this constant, yeah, may depend on t. So we can decompose the part into the part with t is outside as a constant, and then the vector has nothing to do with t. This doesn't work for any solution. This only works for straight line solutions. Still okay? Pay attention here. Y is a vector, V is a vector, Ft is a number. Okay. Now to find which V or which Y, you just need to say, hey, this one also satisfies the differential equation. Y prime equals AY, right? That's your differential equation. If you plug this one in, what do you got? You got Ft V prime equals A times Ft V. Again, only for straight line solutions. Now, interesting thing happened. What happened? Well, because your V is a constant, your prime goes to your Ft. Because Ft is a thing, so you can take it out. You have something like this. Okay. Good so far? Okay. Vector, vector. Okay. Number, number. So what you really have is you want your AV to be a number times your V. Andrew, question?
I'm curious about like what's the significance of knowing what a straight line solution would be like for like an application. Like why would they use it?
The beautiful thing here is like if you have the straight line solution, all the other solution will be nothing. Hold on, let's say this. You only need two solutions. Anything else will be a linear, all possible linear combinations, right? So out of all these pool, you just need two. And the straight lines are the easy ones to find. So how about we just go with straight line solution, and if we have two, we stop there. Everybody else will be just all possible linear combination of these two straight line solution. Kind of makes sense here. Okay, so it's the same idea in linear algebra. If you want to know everything in R2, okay, what do? You say, well, I pick a basis for R2. Which basis do you want to pick? Well, you can certainly pick these two. Okay, but why do we always pick 1, 0 and 0, 1 if possible? Because that's the easiest. Sounds good. Okay, so this is our approach. We will try to find two, and we happen to have two which are easy to find. So why don't we just go with that? Okay.
I just have another question. So if we're working in a three-dimensional space, then we would have three straight lines.
Yes. And then you have three vectors. Okay, let me just go over the whole thing then. Let's say this. If you have two vector in two dimension, two straight line thing, right? Okay. Now what happens is, okay. What happens is on this line, you're going to have something e to the 2t. On this line, you're going to have something e to the 4t. Good so far? So where will the whole thing go? Well, depends on do you have the same speed. If the speed is the same, it will just be on this line. If the speed is different, then this one goes a little bit faster, this one goes a little bit slower. You can see the whole thing was traced like this. It's basically a linear combination of these two, okay? But this in both directions, they go at different speed. That's how you get a curve. So anything like this is going to be a linear combination of the two straight lines we just find, number one. Number two, for any initial value problem, what's going to happen? Well, you want to know what K1 and K2 is, right? But how do you do that? Because every time you have a y, which is k1, y1 plus k2, y2, where these two are straight line solution. Okay, how do you know k1 and k2? K1 and K2 need to work for every t, so you just need to check the initial condition. Which means you take your initial condition, decompose it into two initial conditions on two straight line. You will know K1, K2, then you know everything because these two constants stay the same for any t. Does that make sense here? Now think about 3-dimension, same thing. Okay, you have 3 directions. It's just they go at a different speed. Sounds good? Okay. Very good questions. By the way, I can give you some other thing if you think about this. What's this? This is a straight line solution. Okay. What's this? This is a straight line solution. They have different speed at different t. Still okay? What's putting these two together? It's a circle. Sounds good? So if you think about everything you learned before about parametric equation, it's basically just two straight line solution. What's your solution on x? What's your function on y? What's the whole shape when you combine x and y together? It can be any shape. Sounds good? Okay. The sad thing is this time we cannot decompose them into x and y because x and y are not straight solution anymore. Okay. Some vector are. We just need to know which these vectors are. All right, so that's several ways of explaining this. You're trying to do a parametric equation basically on two bases. Once you have that, you have the whole curve. But now to make the note clean, where am I? I'm here. This is the vector, this is the vector. Okay. From here, you can see you're basically looking for a v, which is a vector, equals to a number times a v. For you to have straight line solution, this one has to be true. For this to be true, your AV has to be a number times v. Still okay? Okay. Does it look familiar? A matrix acting on vector is the same as a number times a vector. The number usually we represent by lambda. That's the eigenvalue and the eigenvector. That's the beauty. Okay. If that happened, what happened? Well, go from here to here. That basically means you have f prime t v equals ft av. But the av is lambda v. Okay. So what do you have? Number one, you have v offers you the straight line solution because now you have a vector. You just multiply the vector by a number. Okay. It is actually the eigenvector of A. Moreover, you have another thing left over. That is f prime t equals ft times lambda. That will be what your ft satisfies. Do you recognize that differential equation? The solution is just e to the lambda t times a constant, of course, where lambda is your eigenvector, eigenvalue. That's beautiful. with that in mind, everything got solved. So now I can write down the conclusion for a straight line solution of this. Okay, they definitely look like this. Where lambda is your eigenvalue and the v is your eigenvector. That's it. All right. With that in mind, let's review a little bit about eigenvalue and eigenvectors, just the basic concept. Eigenvalue lambda, eigenvector v. Okay. The key is lambda v equals AV. Okay. So number one, how do you find lambda? Well, you take AV minus lambda v equals 0. Then you have A minus lambda I. Actually, by convention, let's do lambda I minus V, A. V equals 0. This is the homogeneous equation. Usually it only has trivial solution, and we don't want trivial solution. We want this one to have non-trivial. V. Therefore, so this is how you find the lambda. This is called characteristic polynomial. Let's just call it characteristic equation. Use it to find lambda. Once you find lambda, solve for V. Such that AV equals lambda V. That's how you find eigenvector. All right. Let's try the example. We had this before. That's right. Okay. Through something, we basically identified this one is going to be a solution. This one is going to be a solution, right? This one corresponded with e to the negative 4t. This one corresponds to with e to the 2t. Okay, that's solved by solving them individually. Now, let's solve it in the new way. Then take this out and find the lambda. Lambda I minus A equal lambda lambda minus A okay. Then the determinant this implies lambda equals 2 or lambda equals negative 4. You've done this a lot of times before. Okay. Do you realize it's this number here and this number here? 2 and -4. You got them. Okay. Now the rest is try to find the eigenvector. For now, you're pretty confident. For eigenvector 2, I should get 1, 0. For eigenvector -4, I should get -1, 2. That's the solution, right? Okay, let's try that. Lambda equals 2. That means let V equals AB. We don't know AB. So AV equals 2V. This comes from the matrix on the left. On the right, you have 2V, which is your eigenvector. So what you can have is 3B equals 0, which implies B equal to 0. Therefore, V equals A0 and we know this is subject to a change of constant. So we have 1, 0 times A. This A is just a constant. So first solution 2, this e to the 2t 1, 0 will be my first solution. Now same idea with this. The bottom is useless. -4b equals -4b. The top is 2a plus 3b equals -4a. 6a equals -3b. So we have a and b equals 2a, -2a. Just a times this. So we got the second vector. Sounds good. You have one solution, you have two solutions. What's special about these two? Well, this one always stay on 1, 0. It's a straight line solution. No matter how you change t, you just change the multiple. What's special about this one? This one always stay on 1, -2. No matter how you change it, it just move up and down, but always along the line. So this will be the two straight line solution. Sounds good? Second, once you have these two straight line solution, what's the application? Well, like we said before, your general solution will just be all possible linear combinations of two linearly independent solutions. So this will be all your solutions, but this time we didn't solve it by solving them separately. We solve it once for all using matrix algebra. Okay. Does everything make sense here? Imagine what if you have a 3x3 system to solve in 3 dimension. Well, you have a 3x3 matrix. Ideal case, you will have lambda 1, lambda 2, lambda 3. You have 3 eigenvalues. Sounds good? 3 eigenvalues give you 3 eigenvectors. V1, V2, and V3. Okay, then what's your solution? Your solution is going to be K1, E lambda 1, V1, T, plus K2, E lambda 2T, V, plus K3, E to the lambda 3T, V. Done. Okay, so how to find the solution totally reduced to how to find the eigenvalue and the eigenvector once you know the matrix. That's pretty neat. Well, of course, in general, we find the eigenvector and eigenvalues using computer. Okay, you can see MATLAB, you can take Python, you can take whatever coding language. You will find they always have a function which tells you the eigenvalue and eigenvector. Huge price has been put on people who can do this faster, just finding eigenvalue and eigenvectors because they're so important. And here is part of the reason why. Okay. Is everything clear here? Now, several side things we need to write down. Comments. The first one, let's just take 2x2 systems, right? Well, you need 2 solutions. You find 2 solutions. You do all the possible linear combinations of them. Fine, I take that. The question, though, is, how do you know they are linearly independent? Do you recall anything like this in linear algebra? If not, let's write this down. Actually, they are. The eigenvectors for distinct eigenvalues are linearly independent. So you don't even have to check. They have to. So don't worry, if you find 2, you just go ahead and do it. Guaranteed. Why so? Well, very easy to verify. Let's say we have V1, which is the eigenvalue of eigenvector of lambda 1, and the V2 is the eigenvalue of lambda 2. Okay. Then, what if they are not linearly independent? That must mean V2 equals a constant times V1. If you have more than 1, you can do the linear combination of V1, V2, V3. Still okay? Then what's AV2? AV2 is going to be a CV1 because V2 is a multiple of AV1. Then a constant can be multiplied out. So you just proved where these two actually become V2, right? Good so far? From this, you have to say lambda 1 and lambda 2 must be the same. Otherwise, I'm the eigenvector of lambda 1 and lambda 2 at the same time. It can't happen. So the key here is distinct. Do you also recall something called eigenspace? Okay, that means basically if something is your eigenvector, then all possible linear combinations of your eigenvector is going to be the eigenspace corresponding to this one. So if you have another vector, eigenvector of another eigenvalue, which is a linear combination of this eigenvector, that means it is actually in the eigenspace of this different eigenvalue. So that cannot happen. Sounds good? Okay. Of course, you have trouble then. What if the eigenvalues are the same? Very easy. Okay, what's the eigenvalue here? Lambda equal to 2 for twice. Right? You are supposed to have 2 eigenvalues, but you only have 1. Actually have the same eigenvalue repeated for twice. Okay, how do you do that? Because you only have 1 eigenvalue. For this, we need to do generalized eigenvector. That means we need to find more than 1 eigenvector for the same eigenvalue. We'll save it for later. But just keep in mind, that's a warning. Second, this gives us something even more interesting. For linear systems with constant coefficient, you can always find eigenvalue. That means your solution always looks like this. What is this? Well, depends. It's exponential growth. Okay. It's exponential decay. It's 1. Still okay? Now, let's take the solution we just did. You do know on this direction it's e to the 2t, right? That means you start from here. What do? You go away. Okay. You do know on this one, it's e to the negative 4t, right? That means if you start from 0, 0, you go back as t goes by. Make sense so far? Okay. That means this will be able to tell you source or sink of your equilibrium if you just look at this. Make sense so far? Okay, if it's bigger than 0, source in that direction. If it's less than 0, sink in that direction, because everybody comes back. Okay, So when do you have a sink? You need to make sure from all perspective, all directions, it's all coming back. That means all of your eigenvalue has to be negative. That's when you have a sink. If all eigenvalues are positive, that means you definitely have a source. And if you have some part of them are positive, part of them are negative, that means in some direction you come back, in some direction you go away. Make sense to everybody? It's almost like calculus 3. How do you show that the limit exists? From all different trajectory, it has to be exist and it has to be the same. As long as one direction fail, well, it's not a limit. Or if you're talking about like local maximum or minimum in calculus 3, it should be concaving up in all directions. As long as some direction is concaving up, some direction is concaving down, you have a saddle. It's the same idea here. I will hold onto that conclusion. You see, I didn't write it down because I want to be more careful. But for now, it's just like a idea. Yeah, kind of makes sense though, right? If t goes to infinity, you got 0. So of course, on that direction, you have 0. You trace back. Okay. What about lambda equal to 0? Some matrix look like this. That corresponds to degenerate. You think you have a 2 by 2 system. Actually, you don't. Even though it looks like 2 by 2, it's actually lower. Okay. Finally, do we cover all the cases here? Bigger than 0, less than 0, equals to 0? That's all the real numbers, right? Can eigenvalues be complex? Can it? Can you make it happen? What's this? This is going to be a determinant. What is a determinant? It's going to be a polynomial. Can polynomial have complex roots? Of course. So we do have complex number. Very easy to construct. Okay, let's take that. Let's take this to be 1, this to be 1. Lambda I minus A. Lambda 1, 1. The determinant is, which is still doable, but now if you put a negative sign here, this tells you lambda equals positive negative I. Okay. Then it goes all the way back to what do you mean by e to the a plus bi? I think we had this discussion before. That's going to be e to the at cosine bt plus I sine bt. So do you always have a straight line solution? The answer is no. Do you remember the harmonic oscillator? Recall? Do you have a straight line solution there? No. Why is that? Must be that you don't have a real. Okay, you don't have a real eigenvalue. Therefore, you cannot have a straight line. You have rotations. Okay, if you don't believe so, just take a very easy example. And we prove that, right? This one has a, well, that's exactly the one I wrote down. No, that's not. Let me be careful. Okay. Lambda is complex. No straight line solution. good news is, even though it's complex, we understand what it means. So it's actually really not, it's really not a big deal. The way to do it is the same. All right, that's all we have for today. Okay, let's continue on Friday.